Now we're going to do a derivation of what I call the time-free kinematics equation. The information that it contains is in many ways equivalent to the equation that has time in it. However, there's going to be situations where you're looking at a problem where you don't actually have any time information. Now you might have enough information to calculate time, but using this equation directly is actually a shortcut in a way. It's mathematically going to work out the same way, but effectively the solving for time and plugging in part has already been done for you. Now one thing I want to note is that here I'm showing the form where instead of saying x at the moment of t final, I'm just writing it as x sub f, but that's equivalent to the same thing. So don't be confused that sometimes I write it this way, so x as a function of t sub f versus just x sub f. Same thing. So what we want to do is to not have time in this equation. We have our delta t, our elapsed time. But you might not actually know what that is. So what we need to do is actually come up with a way to get rid of delta t by using a new piece of information. One mistake that I see students make is that they just try to rearrange this equation to solve for t, but mathematically, we literally need another piece of information. Now there's one other little cosmetic thing that we're going to do initially, and that is instead of talking about x final and x initial, we're actually going to talk about the displacement, so x final minus x initial. Okay, so now this term on the left is going to become our displacement, delta x, and we need this new piece of information over here. Now, mathematically, right now we have 1, 2, 3, 4, 5 different terms in this equation. So if I want to get rid of delta t, I actually am going to need to put in a new piece of information. And that piece of information that we're going to be replacing it with is actually the final velocity. So right now we know the initial position and the final position. We know the initial velocity, and we know the acceleration. So what we can do is use that the final velocity minus initial velocity over time is equal to acceleration. This is just the definition. For average acceleration, which in our case, since it's constant acceleration, we can use this. So I'm going to rearrange, so going from here to here is just algebra, and that means now I have something I can replace delta t with. Note again, as I said before, that this final velocity is new. We didn't have that up here. So this is only useful in a situation where you know what your final velocity is, but frequently you might be told that you have an object coming to rest, so you know that that final velocity is in fact 0. Now, also just for aesthetic reasons, we're going to be moving this x final minus x initial and make that be change in x, or displacement. And again, you might be told this information more specifically, like if we're talking about a car slamming on the brakes and coming to rest, we might be told that it skid 100 meters. So that delta x then is equal to 100 meters. So x final minus x initial becomes delta x, and we're taking this term and plugging it in everywhere we have delta t. Now one thing to be careful about here is to not get sloppy in your math, that we had delta t squared. So this term goes inside those parentheses and is then going to be squared. Now at this point you note that we have 1, 2, 3, 4 different terms here. Now again, the reason it's 4, not 5, is before I counted x final minus x initial as two separate ones. So if this is x final minus x initial, that's 2, 3, 4, 5. So we still have 5 pieces of information in here. If I give you 4 of those pieces of information, you can always solve for the 5th one. Now this isn't that pretty of a form, and in fact what we can do is do some algebra, and that's going to get this into a nicer form. Now if you have access to the Knight textbook, Knight gets this far and then says do some algebra, and then shows you the final form. I am actually going to walk you through the algebra. Again, for some of you who maybe it's been a while since you've had algebra, or you feel like your initial algebra class wasn't that great, remembering all of these little steps is important, so I'd like to show you those. So again, the next few minutes is just algebra, but we're going to get this to a nicer form. So one of the things to do here is go step by step. one of the things that you need to start with is distributing. So note that I have this term here multiplied by two terms on top, and over here I have a squared that needs to be distributed. So I've now multiplied my initial velocity up to both terms, and I've explicitly put my squared on both top and bottom. So on the next step, I'm going to start canceling these accelerations. Now be careful because I have an acceleration squared on the bottom, and you can think of this acceleration as a over 1, so this is on top. That leaves me with a single acceleration on the bottom. So this is like having a over 1, and this is like having a times a. So this cancels one of them. So the next step then is to have nothing's changed on this first term, but now I've pulled in that 2, so this 2 has become down there, and this has gone away, leaving me with one acceleration term on the bottom. Okay, so it's not great yet, but we're a little bit closer. The other thing that I did was I expanded this out. Again, please be careful and don't just get sloppy by focusing on the physics, remembering that when you have two terms squared, you can't just say it's this first term squared minus the second term squared. You actually need to multiply it out, and you see that it gets this form. Again, be careful with things like your signs. Your first term ends up with a plus sign, and when you square the second term, minus vix times negative vix gives you a positive vix squared. So please be careful with these sorts of steps. So next what I'm going to want to do is combine these two terms together. Now, you may have learned to do this in a different way, but what I'm going to do is actually multiply everything, so both the left and the right, by 2a sub x. So that will cancel this 2 sub a sub x. That will give me a factor of 2 on top over here, and that will give me a factor of 2a sub x over here. Now again, I have to go on to the next page so that we have a little more space to do this. Okay, so we've gone on to the next page. This is what we already had, and as I mentioned, the next step is trying to get rid of these fractional form by multiplying both the left and the right by 2a sub x. So when we do that, we're left with 2a sub x, delta x on the left, that's okay. We're left with a factor of 2 on this left term, and again, I'm writing it out explicitly this way because you must distribute it, and on the right, we're just left with the term on the top. So not too bad. Now we're going to distribute that 2, and we're going to start canceling. So 2 goes in front of both of these terms, and now note that at this point, this still doesn't look really good, but I have 2 v final times v initial, and then over here I have a negative 2 v final v initial. So I actually get to cancel those. Also note here that I have a vix squared and a vix squared, so I can combine these together, but be careful because I have a kind of a plus 1 here and a negative 2 there. And so when I can't combine those together, I actually end up with negative 1 vix squared. Don't lose this other term here. So now I'm left with this single term on the left and 2 terms on the right. This has actually gotten much simpler, right? So now there's a different way we typically write this that mathematically is just equivalent, but that is to rearrange and have the final velocity by itself, and that means moving this over to the other side, and that would give it a positive sign. So that's all that happened here. So this is the final form of the equation, which you can see is fairly simple, and I would call this the time-free kinematics equations. You need to know what your final and your initial speed are. Frequently, one of them might be at rest, so that would be 0. Then you have the constant acceleration. Again, this is only true if you have constant acceleration, and the displacement. Again, be careful, remembering that this displacement term here is going to be your x final minus x initial, so don't just put one of those values in here. And there is this factor of 2 hanging out, which was due to the 1/2 term in the original one. So that's the derivation here. Again, mostly just algebra, but this form of the equation can be really helpful if you're working towards a situation where you weren't given time, you don't need time if you have these pieces here.